All right, it's time to start organic chemistry. So we're doing a crash course here. This is going to be pretty quick. But today will just be the introduction, and then in the next couple of days we'll just run over some of the stuff that you need to know for the AP exam for organic. There's not a ton on the test, but they tend to try to work this in with a lot of other types of problems. The types of problems that you'll usually see it worked in with usually have to do with intermolecular forces or maybe what's the shape of the molecule or the hybridization. So that's why we're talking about organic chemistry in this particular unit, because it fits in well with the stuff that they like to combine this with on the AP test. So when we talk about organic chemistry, you might or might not be familiar with this, but organic, we're just talking about things that are alive, okay? And typically our definition of something that's alive is something that has these carbon compounds that lead to the formation of DNA and nucleic acids and stuff like that that lead to the formation of life. So that's organic chemistry. When we talk about organic chemistry, I want you to think carbon and hydrogen mainly, and then you've got other stuff tacked on there, but carbon and hydrogen, that's really the main backbone of any organic molecule. Okay, carbon has the ability to form very long chains because it has this sp3 hybridization ability that we talked about earlier, because it's got if you talk about the orbital diagram for carbon, you've got the 2s orbital, and then you've got the 2 p's. And when it promotes one of its electrons, then what you end up with here is something that has a half-filled s and 3 half-filled p orbitals, and that's very conducive to forming 4 different bonds around the carbon. Okay, now carbon can't expand its octet; it's only in the second period. But this is just, it's a good electron configuration for forming 4 bonds very often around the central atom. So if you just keep building on these carbon atoms, which can each form 4 bonds, then you've got all kinds of structural possibilities. So again, when we're talking about organic molecules, we're talking about things like proteins, lipids, carbohydrates, nucleic acids. These are some of the main categories of organic molecules, and all of these have carbon chains as their backbone. So the structure, again, there's 3 different possibilities here depending on whether you have double bonds or just all single bonds. If you've got all single bonds, then it's an sp3 hybridized. That half-filled s and those half-filled p's all hybridized to form 4 domains around the central atom. So then you get something that's tetrahedral in shape, like this structure on the left here. Okay, CH4 is a really good example of that. Methane. Tetrahedral arrangement, you've got 109.5 degree bond angles, and you've got the sp3 hybridization. Okay, if you have a double bond on the central carbon, then it's an sp2 hybridization, and the shape is going to be trigonal planar. You're going to have 120 degree angles. And then if you have a triple bond on that central atom, then you're going to have a linear structure. Okay. Now you could have 2 double bonds also, like carbon dioxide, which we don't count that as an organic molecule, but that would also be linear. So there are a lot of different configurations that you can have around this thing, but the 3 different shapes that can be formed around a central carbon atom are the tetrahedral, the trigonal planar, and the linear. And just depending on how many single or double bonds or triple bonds you have. Carbon-hydrogen compounds, they tend to be stable and unreactive. Carbon and hydrogen are very similar in electronegativity. If you actually look up the electronegativity value for both of those things, they're very similar. So when those 2 things come together, there is a little bit of polarity there because obviously they're different atoms. But this is not a very polar bond, the carbon-hydrogen bond. In fact, most of the time, the difference in electronegativity is so low that we consider the electrons to be shared fairly equally between the two, which makes it fairly stable. Okay, and we'll talk about this again at the end, but because they're not polar, they tend to not dissolve in water very well. Okay, so any organic molecules you can think of, I know you guys worked with DNA in biology. I'm pretty sure that you worked with DNA in biology, and you had to dissolve that DNA in alcohol because it doesn't dissolve very well in water, because it's not that polar. Anytime you're trying to wash fats off of your plate from dinner, that sort of thing, if you've ever tried to get butter off of your plate, you might have noticed, or even off your hands, or grease or anything like that, you probably noticed that doesn't wash off very easily with water. Now, if you use hot water, you can actually melt it, because usually the melting points of these things are pretty low. But a lot of times, if you're just using cold water, you have to use soap in order to get these off, because they don't dissolve very well in water. And that's because they're not very polar. And so polar water is going to dissolve other polar things. Non-polar dissolves non-polar. Honestly, I can't remember if we talked about that last year or not. We're going to talk about it in the next unit. Alright, actually, I guess in 2 units, if we didn't talk about it last year. Okay, so 4 basic types of hydrocarbons here: alkanes, alkenes, alkynes, and aromatic hydrocarbons. Okay, the first 3, obviously sound very much alike. You're just changing one letter. Okay, and the alkanes, we're talking about carbon-hydrogen compounds that only have that only have single bonds. Okay, or only sigma bonds is another way to say that. The alkenes, we're talking double bonds, at least one double bond in the compound. And then alkynes, that's at least one triple bond in the compound. And then aromatic hydrocarbons, those are the ones that are ring structured. They're called aromatics because a lot of times they have these very strong, recognizable odors to them. Okay, and actually a lot of times they're very good smelling molecules. So benzene smells kind of like roses. I remember my organic chemistry teacher telling us that he was quite a bit older, and he said when he was in the lab in college, he would play with benzene, not play with it, but they would get it all over themselves, and when they were doing labs and that sort of thing, they always enjoyed the smell, and it's like afterwards we always smelled so good. And then they found out that benzene causes cancer, so that wasn't good. So they stopped, getting it on themselves at that point, or we're a little more careful with it. But anyway, these aromatic hydrocarbons, a lot of them smell really good, or have some distinctive odor to them. But the main thing that defines them is that they have ring structures. So you can look at this benzene, for example. It's a hexagon. Okay, so you've got all these carbons arranged in a hexagon, and then you've got hydrogens attached to them. Okay, so the main thing we're going to talk about today is alkanes. And these are the simplest kind of organic molecules. They only have single bonds. So ethane is a good example, CH3CH3, and a lot of times that's called C2H6. But the CH3CH3 thing sort of gives you a better idea of the structure. You've got, one central carbon here with 3 hydrogens around it, and then another central carbon over here with 3 hydrogens around it, and each of those are tetrahedral in their arrangement, because they're surrounded by 4 other atoms, 4 domains, bonding domains, and so they're each tetrahedral there. These are called saturated hydrocarbons. So these are saturated with hydrogens. That's why they're called that. They have as many hydrogens around them as they can possibly have. So saturated fat, unsaturated fat, that's where this comes from. It has to do with whether you have only single bonds or if you have some double bonds as well. Okay, and we'll talk more about that when we talk about alkenes. The Lewis structures are going to look similar to this. Okay, this is a 4-carbon chain with hydrogens all around it. They're pretty simple to write the Lewis structures for. You basically just have to build a line of carbons and then add hydrogens everywhere to make sure that there's 4 things around each carbon, and it usually works out. These are called structural formulas. Okay, but a lot of times these are just really painstaking to write, especially when you get up to something like decane, and now you've got 10 carbon chain and you're trying to put all the hydrogens around it. So we can also use something called a condensed formula, okay? And that's what's shown on the right over here. And the condensed formula, it still does an okay job of showing where the hydrogens are connected, but it's not quite as labor intensive. You can still tell that there's 3 hydrogens around this outer carbon here and around this outer carbon here, and that there's 2 hydrogens on the inner carbons. But you don't have to actually draw out the whole Lewis structure like you have over here, so it's a little bit quicker. It's kind of a nice shortcut. So if they ask you for the Lewis structure, they're looking for the thing on the left. Okay, if they ask for condensed formulas or condensed structures, then they're looking for the thing on the right. All right, so here are the first 10 alkanes, and these are the ones that you actually need to know the names for. I'm going to give you a really easy way to remember this, at least the first 4, because the first 4 I think are the hard ones. Methane, ethane, propane, and butane. Okay, methane is 1 carbon. Ethane is when you have a 2 carbon chain. Propane is when you have a 3 carbon chain, and butane is when you have a 4 carbon chain. So if you just remember this little acronym, meet, Ethan, professional, put a comma there, professional butler. Okay, meet, Ethan, methane, ethane, propane, butane. Okay, meet, Ethan, professional butler. And that gets you the first 4. After that, they sort of make sense because pentane, pent, you know, that's the prefix for 5. Then you've got hexane, 6, heptane, 7, octane, 8, nonane, 9, and decane, 10. So the rest of those really make sense as far as their prefixes. But the first 4, if you remember meet, Ethan, professional butler, that will help you remember the first 4. So the only van der Waals force, so the only intermolecular force that's present here is the London dispersion force, because these are completely non-polar. If you look at them, it's just carbon and hydrogen. The boiling point is going to increase with the length of the chain, which we talked about the other day. That's one thing that really affects the London dispersion. Not only do they get longer, but they're getting more massive. So these are, you know, the decane is a long, skinny chain, and it's also the most massive of all of these. So the decane is going to have the highest boiling point. So you have to get it quite a bit hotter in order to get it to boil. When you look at things like methane, ethane, propane, and butane, those are going to tend to be gases at room temperature. And then once you get into the pentane and down, those are going to be liquids at room temperature instead, just because they have much higher boiling points because they're longer chains and they're bigger. I don't think I need to talk about that anymore. So in alkanes, we're talking about sp3 hybridization, okay? Because each of these carbons is going to have 4 bonding domains around it, okay? So this is going to have a tetrahedral shape and 109.5 degree bond angles, give or take. Now, yeah, they're going to be right at 109.5. I was going to say it depends on what's attached to it, but if something else is attached to it besides just carbon and hydrogen, it's not an alkane anymore. Now it's something else. So there's only sigma bonds in alkanes because we only have single bonds, so there's no pi bonding. What that means is there's free rotation around the carbon-carbon bonds, okay? In other words, I can take this molecule and I can sort of spin it in certain places, and it doesn't really change the arrangement. And so you've got this, you know, this carbon-carbon bond right here. I could spin this thing around, okay, and it wouldn't really affect the nature of the molecule at all because there's only a single bond there. Now, if I had a double bond here or a triple bond, that holds the molecule more rigidly in place, and now this thing can't spin anymore. But because these are just single sigma bonds, they're a little bit more free to rotate, okay? And so you just kind of have to keep that in mind. And we'll come back to that again when we talk about alkenes and alkynes. So you can have different isomers here, and this is one of the trickiest parts about this is knowing the isomers. But an isomer, it would have the same molecular formula, but the atoms have a different order to them. Okay, so an example of this, butane is just 4 carbons right in a row, and then you've got the hydrogens around it. Okay, now isobutane is an example of an isomer. Okay, and so if you look at this, it's still got the exact same formula. Okay, so the formula for butane is C4H10. Okay, that is also the formula for this molecule over here, C4H10. If you count up all the carbons and all the hydrogens, it's the same. Okay, but they're arranged in a different way. So this is called an isomer, because now you've got a 3-carbon chain, and then you've got 1 carbon coming off of the end there. Okay, same thing with pentane. You've got a 5-carbon chain for pentane, and then there's a couple different isomers, possible isomers down here for pentane. And now they all have the same formula. Okay, they're all C5H12, I believe. Okay, all of them have that formula, but they have different arrangements. So that's an example of isomers. Okay, so they might ask you this kind of question on the AP exam, and you have to figure out, given this molecule up at the top here, this butane molecule, which one is an actual isomer. Okay, and you should try to do this without looking at the screen before. But basically what you've got here is our first option is a 1, 2, 3, 4, 5 carbon chain. Okay, well, that's not an isomer of butane because there's 5 carbons there, so it's not going to have the same formula, right? This is going to have a formula C4H10, like we just talked about. So this first one is out because that has a C5H something. Okay, this second one here, 1, 2, 3, 4 carbons, so that's C4. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H10. Okay, well that's looking promising right there. And that's in a different arrangement, right? Because there's a carbon coming off of this. There's basically this carbon in the middle here is connected to 3 different carbons. Okay, and that's not the way that it is up here. So that one is an isomer. Okay. Now it's asking which of the following. So which of the following is an isomer. So this is probably our only one right here, but we can check the last one just to make sure. The last one has, again, 5 carbons, so that's out. Okay, so that's how you identify an isomer. You're looking for something that has the exact same formula. Okay, now we need to talk about how to name these things, and this is a little bit tricky. This is a different system of naming than you guys have used before, so this will take a little getting used to, and there is some memorization on the rules here for how this works. Okay, so there's 3 parts to a compound name. The base is going to tell how many carbons are in the longest continuous chain. Okay, and I'll show you what that means in just a minute. The suffix is going to tell us what type of compound it is. And we're not really going to talk about the suffixes today. That's when we get into functional groups and that sort of thing. What else is attached to it? But then the prefix tells us what groups are attached to the chain, what substituents. And again, I'll show you what that means in a second. But that essentially means what things are coming off of the main chain. Okay? All right. So here's the name of the groups. These are the prefixes that you're going to put in front. Right here, and these are the main ones that you'll have to know. Really, honestly, if you know methyl, ethyl, propyl, and butyl, and maybe isopropyl, then you're probably fine. I don't know that you need to know the tert butyl. I've never seen that one show up on an AP exam. But the idea here is you're going to find the longest chain in the molecule. Okay, so if you're looking at a molecule like this one up here, then the longest chain, you could start by counting at this carbon, 1, so they call this one number 1, 2, 3, 4, 5. It doesn't matter which way you start it, okay? They're choosing to start on this carbon right here, okay? But you have to figure out which one gives you the longest chain. Both of those ways would give you 6 carbons in the longest chain, okay? And so basically what you're doing here, you've got 1, 2, 3, 4, 5, 6 carbons in the chain. Okay, so they box this in because this is your main chain here of carbons. Okay, and then off of that main chain there is one group here that's not part of the main chain. Okay, and so you have to name that group. All right, so first of all you're going to find the longest chain. Then you're going to number the chain from the end nearest the first substituent. Okay, what that means is I don't want to start numbering over here 1, 2, 3, 4, 5, because if I do that, this group right here, I don't get to that group until carbon number 5. Okay, and if I number it in the direction that they numbered it, erase some of this stuff, then I get to this group right here by the second carbon. So I want to number it in such a way that I get to the substituent, which again, that's the thing that's coming off of the main chain. So I get to that substituent as quickly as possible. Okay? So then the next thing, I'm going to list the substituent as a prefix along with the number of carbons to which they are attached. Okay? So this one's attached to carbon number 2, this CH3 right here, and according to our chart down here, CH3 is a methyl group. Okay, so we're going to call this 2-methyl hexane. Okay, the hexane comes from the fact that there are 6 carbons in the longest chain, and then the 2-methyl part comes, well, the methyl part comes from the fact that this is CH3, that's a methyl group, and it's connected to carbon number 2, so we call it 2-methyl hexane. Okay. If there is more than one type of substituent, you need to list them alphabetically, which is weird because you might think that you would just list them numerically, you know, whichever one you get to first, but you're supposed to actually list them alphabetically. Okay, so on this one, this first one here, our second example, I guess, our longest chain here is this one. And this chain, when we draw it this way, or when we follow this chain, it gives us 7 carbons. Okay. Now there are a lot of groups coming off of these. Okay. And the reason we numbered it this way, starting with the 1 down at the bottom and then up to 2, is because our first substituent group comes on carbon number 2 if we number it this way. If we numbered it backwards, if I made this carbon number 1 and this carbon number 2 and this carbon number 3, then we wouldn't get to our first substituent group until carbon number 3. Okay, and so you have to name that in such a way, or you have to number it in such a way that you're getting to the substituent first, or as quickly as possible. Okay, so this one is crazy as far as its name. We've got 1, 2, 3, 4 substituent groups on this one. Okay, this is a 7-carbon chain, so we're going to call this one heptane. There are 3 methyl groups on this thing, and that's these 3 right here, 1, 2, 3. And then we also have an ethyl group, one that has 2 carbons coming off of the chain. Okay, so the ethyl group comes first because alphabetically it's first in the alphabet. So we're going to call this 3-ethyl because the ethyl group is coming off of carbon number 3. And then we're going to call it 2, 4, 5 trimethyl. Okay, and again, why do I have to put the tri there? I think that's kind of dumb, because if it's 2, 4, 5 methyl, then obviously I have 3 methyl groups, but you also have to put a prefix there, trimethyl. Okay, and the prefixes you use there are the same ones that you use when you're doing covalent compounds. So again, there's a lot to remember here. This gets kind of crazy, but you do need to know how to name these alkanes. So let's see here. The other thing to notice is the dashes. Okay, the dashes go in between the numbers and any of the actual writing. Okay, so you've got 3 dash ethyl dash 2, 4, 5 dash. Okay, so between the numbers and any of the actual name, you need to put dashes like that, and then there's commas in between any of the numbers that come in sequence because you have more than one of the methyl groups here. All right. So again, I know this is a little overwhelming. The other thing you need to know, if there's an N in front of the name, they're going to throw this at you sometimes on the AP exam, like N-butane. That's the same thing as butane. It just means it's an unbranched chain of carbons, okay? I really don't know what the N stands for. You could think of it as normal butane, normal ethane. I don't think that's what the N stands for, but basically it's just the normal structure, the normal isomer there, where you've got the carbons all in a chain, so it's just the normal thing. So don't let the N-butane throw you. That's just butane. N-ethane is just ethane. N-pentane is just pentane. Okay, so let's practice here a little bit on naming these things, and this takes some practice. So we've got this alkane right here, okay? Now this obviously is a branched alkane. It's got some groups coming off of it. So the first thing we need to figure out is the longest chain of carbons here, okay? And it looks to me like if we start up here and kind of work our way down. Now this could go one of two ways. I could either go down here, or I could have traced that across, because this is going to be the same thing, basically, if I had gone that way with it. So it doesn't, ultimately it's not going to matter when you're naming this thing. If you have two different ways you can pick that gives you the exact same number of carbons in the chain, then you can go either way, and the name will end up being the same. Okay? So, let's see here. So what we want to do here is we want to just number these things, and we want to number it in such a way that we get to the substituent as quickly as possible. Okay, and I'm just realizing I drew that box incorrectly. It needs to go like this. There we go. Okay, so that makes more sense than what I drew before. I cut off one of the bonds before. So then we're going to just number this thing, okay? Now if I start by numbering this as 1 and 2, and then this one would be 3, then our first substituent group comes right here on carbon 3. Now if I number it from the other direction, if I start on this carbon, 1, 2, 3, 4, okay, then our first substituent group would come at carbon 4. So I've got to number this from the bottom up. This is 1, 2, 3, 4, 5, 6, 7. Okay, we have 7 carbons in our longest chain. So immediately we know we're going to call this heptane. So, there we go. Heptane. Okay. And then we just need to figure out what prefixes to put in front of this based on the substituents. Now this one's not too bad, because we've got 1 here and we've got 1 here. Alright? And these are both methyl groups. And so when we name this thing, we're going to call this 3, comma, and then the other methyl group comes off of carbon 4 here. So 3, 4 dash methyl heptane. Okay? And that's how you name that. Right, the condensed structural formulas for N-octane and for 3-ethyl-2-methylpentane. Okay, so now we're going backwards. They're giving us the name. We have to write the actual formula. Now, condensed formulas is what they want here. So you can start with the Lewis structure if you want to. Sometimes that's helpful just to know how many hydrogens we're actually going to have. And then you can write the condensed from there. So I'll probably do that on this one, just to give you an idea. Octane has an 8-carbon chain. 1, 2, 3, 4, 6, 7, 8. And then we've got hydrogens coming off of all of these here. And again, this takes a while, which is why the condensed formulas are a good thing. But when you're first learning these, it's probably a good idea to write out the full Lewis structure just to make sure you get the right number of hydrogens on everything. okay? So the condensed structural formula for this one is going to be CH3, and the next carbon has 2 hydrogens attached to it, so CH2, 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 2, 3, 4, 5, CH2, that's 6, CH2, that's 7, and then the last carbon here is CH3, okay? So that's the octane. Now the 3-ethyl 2-methylpentane, I'm going to have to erase all of this and give myself some room here. Again, I'm going to write this as a Lewis formula first. So pentane is my backbone on this one. 1, 2, 3, 4, 5. Okay, and then I need to figure out what substituents I have coming off of it. Whatever I decide is my third carbon's always going to be this one, the middle one here, regardless of which direction I go with this. So 3-ethyl, okay, so I've got an ethyl group coming off of here, which an ethyl group looks like that. It's going to be a 2-carbon chain, okay? Sorry, change my mind. I'm going to have more room if I write it this way. And then 2-methylpentane. So I'm going to have a methyl group coming off, and I'm going to put that one going up just again so I have more room here. Okay, so that's my methyl group. And then I just attach a bunch of hydrogens to everything. Okay, so this one's got a hydrogen here, here, and here, so that it's bonded to 4 things. This carbon is already bonded to 3 other carbons, so I just need to put a hydrogen here. This methyl group is going to have 3 hydrogens. This carbon is only going to have 1 hydrogen because it's bonded to 3 other carbons. This was bonded to 2 other carbons, so it's going to have 2 hydrogens. This is going to have 3. And still don't have enough room here. This carbon's bonded to 2 hydrogens, and the one on the bottom here is bonded to 3. Okay, so if I'm writing the condensed structural formula for this one, what I'm going to write here is CH3. I have room for this. The next one is just CH, and then off of that I have my methyl group, which is a CH3. Okay, and then my next carbon, I've just got CH again, and off of that is my ethyl group, which is CH2. Well, actually, I guess I'm going to write this the way we normally write this. It's going to be CH2, CH3. Okay. And then I've got my CH2 after that, and then CH3 after that. Okay? So that's what my condensed structural formula is going to look like for that one. So again, writing the Lewis structure is probably a good idea first when you're just getting the hang of these. Okay, structural formula for the 5 isomeric hexanes, and name them using the organic naming system we just learned. Well, that's intense. So the 5 isomeric hexanes. Okay, in other words, we want to talk about the 5 different isomers that can be formed from the hexane chain. All right, so hexane, if you look back, or even just think about it, I mean, hexagon, that's 6 sides, so we've got 6 carbons here. Okay, so the easiest chain to write, and this is not nice because they're saying the structural formulas instead of the condensed formulas, so now you do have to write all the hydrogens. 1, 2, 3, 4, 5, 6. So we're just going to fill in all the hydrogens here on this. Okay, so that is our normal hexane. That's just in hexane, okay? That's our normal long chain. Now, the next isomer that you could possibly have here, you could have a 4-carbon chain, and you could have the other substituent in a few different places, okay? Or I guess a couple different places. So if we've got a 4-carbon chain here, and actually I'm going to skip the writing of all the different hydrogens on the rest of these just for time. So you can hopefully get an idea of what's going to happen here. You just have to fill in the rest of the hydrogen on most of these. Okay, so we've got a 4-carbon chain, and we could have a carbon right here as a substituent. Okay, so that would be called If we number this from this side, 1, 2, that would be called 2-methyl, and this is a 4-carbon chain, so that's butane, 2-methyl butane. Okay. Now, you might think that there would be another way to write this one if we put the carbon on substituent on that carbon instead, but that actually ends up still just being 2-methyl butane because you would number it from the other side on that one. Okay, so that's not one of the isomers. Another possibility here is you could have a 3-carbon chain, and you could have 2 carbons coming off of the central one. Okay, and so that's going to be the way that we would name that one. The longest chain is going to be 3 on that one, so that's going to be propane. And then we've got 2 methyl groups coming off of that second one. So this is actually called 2,2, ran out of room, dimethyl propane. There's supposed to be a dash there. 2,2-dimethyl propane, because these are both coming off of carbon number 2. Okay. We're really short on time here. Okay, they're not going to ask you anything like that where you have to come up with all 5 of the isomers. If you want to try and figure those out, you can. It's kind of a fun little puzzle, but hopefully that gives you the idea, and I'm going to skip on just for the sake of time. But basically, that's how you name these things, and that's how these isomers work. Now, notice in each one of these, there are 6. Wait a second. No, there are not. That's why I was having trouble. Okay, so all of a sudden, I started going to a 5-carbon system instead of 6. So sorry about that. Oh crap. Okay, again, I'm going to leave this as a puzzle for you guys because I just don't want to take up too much time with this. But this one actually, because we've got 5 carbons in the chain here and then 1 carbon down below it, this is going to be carbon number 3, and this is one possible configuration that could happen. And so this one would be 3-methyl pentane. Yeah, sorry about that. So then you could also put the carbon here, okay? But then putting the carbon here would be the same as putting the carbon here. So that's one other one. And then you could do one like this where you had them in the middle, or you could do 2 structures like that where you had them in the middle. So anyway, hopefully that makes sense. Sorry that took so long. Okay, real quick, cycloalkanes, what we've got here is just rings, okay? Carbon can form these ringed structures like a hexane, a pentane, or a propane. Now, propane doesn't, cyclopropane doesn't usually happen that often because it sort of starts to strain the bond angles a little bit. We want to be as close to a tetrahedral as possible, okay? And these 2 bond angles are decently close to tetrahedral. Once you get here, now we're talking about, 60-degree angles on these, okay? And that's not very close to 109.5. So we're really kind of stressing the molecule when we put it in a triangular form. So that doesn't form very often, okay? And then just reactions of alkanes. We already talked about this. They're typically very unreactive because they're almost completely nonpolar. So they actually make good solvents to dissolve nonpolar things in. Gasoline, oil, that sort of thing. Those will dissolve nonpolar things really well, as opposed to ionic compounds, stuff like that, which is better to dissolve those in water. Okay? Alright, we'll talk about this more in class. Sorry that one got long. The naming takes a little while, but hopefully you guys will pick up on that. And we'll do some practice on that in class tomorrow. Alright, see you then.